Hello, my name is Niehues, and I'm at the Karlsruhe Institute of Technology in Germany. I'm very glad that I can today talk to you about neural machine translation and the research we are doing there. I'm sorry that I wasn't able to give this presentation during the conference, but I hope that I can give you an overview about the work we are doing in Karlsruhe through this presentation. We are interested in building neural machine translation systems that have different abilities, for example, to translate different languages, and especially how we can build these systems so that they are able to combine their abilities in new ways, in a plug-and-play way, so that they can solve tasks which they haven't seen during training. To motivate this, we have seen that neural machine translation has really reached a very good quality. We are talking now about systems that are at least comparable to what partly humans can do. This, of course, is only the case if we have large amounts of training data and if we are building dedicated systems for exactly this task. However, neural machine translation systems have another very interesting advantage. While before we are building dedicated systems for each possible language direction, we can use multitask learning to build now a single neural machine translation system that can perform several tasks. So it can, for example, process different languages or process the same language in different modalities, like translate from text and translate from audio, and then it can also generate different languages and thereby translate into different languages. One very successful use case of this idea is multilingual machine translation. In multilingual machine translation, the motivation is that in the world we have around 6,000 to 7,000 languages. However, if we're looking on what people are addressing in research, it's still that most of the research is covering maybe the top 10 languages. In order to build really machine translations between many of these languages, it's very important that we develop a method that minimizes the human effort, so that it's no longer that complicated to build a translation system for all these translation directions. And furthermore, of course, also that need less training data, because we won't be able to generate as much training data for many of these directions as we have currently for the high-resource languages. And one very successful approach in this is the multilingual machine translation system, where we have one model which can translate between many languages. So we are no longer having a dedicated system, but for example, as shown here in example, we could have a system that can translate from English, from German, or from French into all these three languages. The nice thing is that in this case, this model can share common knowledge between the language, and thereby we can then increase the efficiency. So how does this look like? So imagine we are having training data from German to English and from English to French. We can now train one model with all this training data, and then it will be able to generate also English translation of German input and French translation of English output. We can typically control this by having a start token when generating the translation, telling the system, okay, now please generate an English output, or now please generate a French output. Similarly, we can use a similar idea also having different modalities. For example, if we want to combine automatic speech recognition, where there's English text, English audio coming in, and we generate English text, and a text translation where there's an English text input and we're generating French. So here we have now the possibility that we have a single model which can perform several tasks. These models have included different abilities to perform these tasks. So they can process different languages and they can generate different languages. So if we are going back to example, if we are training it from German to English, it has the ability to somehow process the German input in order to understand what is in the text, and based on that, generate an English translation. It has also the ability to process English text and then generate in French output. However, in most cases, these models need end-to-end training data. That means they need training data for each of the possible tasks that we want to fulfill. So they need training data from German to English, and they need training data from English to French. However, in real-world scenarios, we are often not able to collect end-to-end training data for all possible language directions. And therefore, it would be nice if the model is able to combine its abilities in new ways to also solve tasks that it hasn't seen during training. And we are normally talking about this as zero-shot translation. That means we want to recombine the abilities of the model to perform a new task. In our example, it would be that it now processes German and tries to extract the information from the German and then generates French instead of English. Then we would be able to also translate from German to French without having any training data directly between them. However, if we are looking at that, we are seeing that the models often don't really perform well in this condition. And a challenge we believe here is that the representations are not matching. So the representations, how the neural network represents the German text, is different from the neural network representing the English text. And thereby the component which generates French is only used to the English representations, but not to the German representation. So the first way would be, the first question is now, are these representations different? And therefore, we looked into this. We tried to verify the properties of the hidden representations, so the output of our encoder. And there is one approach which has been used for many tasks to inspect the hidden representation of a neural network. So what we are looking here is a transfer learning approach. That means we are taking our neural machine translation system, we are freezing this neural machine translation system, and then we are training a classifier on the hidden representations of our encoder, as shown here. And this classifier should identify what is a source language. And the question is, if this is very easy, then it means the representation of the encoder for different languages are also very different. And then, of course, then we have the scenario where we described before, that it's not easy to use now a different decoder for a different language because it has never seen this type of input. However, if these representations would be somehow more similar, then it would be possible to just switch to the decoder and generate a language which we haven't seen in training. So we looked at this and trained these classifiers. We have done this not only for 3 languages, but for a multilingual setup where we have 8 different languages. And we're seeing here in dark, you see that there is a lot of confusion. In light, there's nearly no confusion. So we're seeing it's nearly always classifying each language correctly. So if the input was German, it classified it as German. If the input was Danish, it was classified as Danish. We're seeing, maybe you see that a bit of confusion, for example, between Spanish and Portuguese, but it's really, really slight. So we are seeing, okay, these representations are really different. So in the following of this talk, we wanted to investigate, can we increase the similarity in order then make these systems able to recombine their abilities in a plug-and-play way? And there is one way of how people have done that before. And that is what is referred to as pivot-based translation. The idea here is that we are not using a neural representation to shift, but we are just using English. So we are always first translating to English, and then we are translating to the target language. So in the case before, we would translate from German to English, and then from English to French. In this case, we do not need any direct training from German to French. Another use case for this is the cascaded approach in speech translation, where we first do ASR, and then in the second step, we are doing machine translation. While we have the advantage that we don't need any end-to-end training data in this case, we also have the disadvantage that we have additional ambiguities. Because we are generating English, and English is a natural language, which will introduce additional ambiguities, it means that we typically lose in performance. So we wanted to invest, can we prevent that, and instead use a continuous representation in between. So the idea is that if we have a language agnostic representation, that we can train our model on German to English and on English to French, and then change our abilities and directly translate from German to French. And as I motivated before, in order to achieve that, what we need is that we have a similar representations for the different languages. So if we put in the German sentence, or if we put in the translation into English as input, it should be that these two representations are very similar, because then in both cases, the French decoder can generate the correct translation in French. So why are these representations are different? And one challenge is already the different word order. So typically, the word order in different languages is also different. For example, in English, the verb is typically at the second position, as shown here, while in German, it's sometimes at the second position, but sometimes it's also at the end of the sentence. And then in our neural architecture, we have a bias that we have a one-to-one correspondence between the word and the hidden state. That means the information about the first word is mainly encoded in the first hidden state, and the information about the second word is mainly encoded in the second word, and so on. And then, of course, these representations will be different because the information about the verb is mainly in the last hidden state in German, while it's mainly in the second hidden state in English. First of all, we wanted again to check if this hypothesis is correct. So we did a very similar analysis, and we trained a classifier on each of the hidden states of the encoder to predict which was the word which was in this position and what is the current position. So we take a single hidden state and try to predict that. And we only train this simple classifier, and the whole of the encoder is frozen. And as you see here, the model is nearly perfect in reconstructing both the word or the position. So we are seeing that there's really this strong correspondence that most of the information of position N are encoded in hidden state N. So we, motivated by that, we were looking into, can we disentangle the position and information? So can we generate hidden representation, for example, where information about the verb is always encoded maybe in the first position, and that is language independent. So it's not that these are different positions for German and for English. And therefore, the question is, the first one is, why is this happening? So why do we have this strong correlation between the word and the hidden representation? And we were assuming that this is partly due to the residual connections. So these transformer encoders typically have many layers. And in order to train them, it is essential to have residual connections, which are a shortcut connection, so that the input of each layer is added to the output. And then, of course, each layer is only modifying this representation a bit. And therefore, we are seeing that, of course, there is like most information is kept at the same position. So these connections are essential for learning. However, they are leading to a bias that we have a one-to-one correspondence. In other use cases, this bias is very helpful when we're doing, for example, sequence labeling with an encoder. It's important to have this bias. However, if we want to have similar representation, it might be a drawback. Therefore, we looked and we investigate how we can remove these residual connections. It was shown that it's not possible to really remove this residual connection in all possible layers, but it was enough to just remove it once in the middle, because then information can be shuffled and we're able to more distribute the information. So first, let's have a look. Does that really happen? So again, we removed the residual connection, trained our neural machine translation system, and then analyzed again how good is the model able to reconstruct the position and the source word. And the results are here shown in the second table. You see, we see, first of all, a very clear draw. So while it was nearly perfectly able to reconstruct, now we're down to around 50%. Of course, it's still relatively high because, yeah, you have typically a sentence of maybe 10 words. So you have maybe 10 possibilities. However, we are seeing that information got distributed very different now than it was in the baseline. So this single change of our architecture allows the model to learn representations which are no longer that position focused as they were before. A second idea that people have investigated, and we try to integrate it partly, is to directly increase the similarity. That means we can add the similarity between, for example, the German and the English representation as an additional loss. And then we are trying in parallel to improve our translation quality. We are having as a side constraint that we should also make these representations as similar as possible. Here's one problem. Typically, sentences in English and in German do not have the same length. Therefore, we cannot directly compare the hidden states, because in German we might have only 5 hidden states, while in English we have 6, for example. Therefore, this is typically done by several people by doing mean pooling, so that we are building the mean of the representation of the English and the mean of the representation of the German, and then we are combining them and thereby trying to get a representation which is as similar as possible. A third possibility is to look into adversarial classifiers. That means we had already in the beginning for the analyze this classifier which tries to predict what was a source language. And now we can use this idea and try to make a representation where this classification task is as hard as possible. So we can have again an additional loss which tries to learn representation so that later the classifier is as bad as possible. Again, this is motivating in having a representation where there's very few language information left. And again, this is then a side constraint, an additional loss, which we can use. And in this case, we can do it on each position so that we are able to really make each hidden state as language independent as possible. Okay, now we have talked about different way of doing it. So let's have a look how well they are working. Therefore, we evaluated these methods on 3 different data sets. In all of these data sets, English was a pivot language. So we always had only parallel data between English and the other languages. In IWSLT, it were 3 languages. In Europal, it was 8 languages. In both cases, it was European languages. And in the PM India dataset, it's English is central, and then parallel data to Indian languages. We are here evaluating using the blue score. And first, you see the baseline results. where we're just using an out-of-the-box transformer neural machine translation, we're seeing that in this case, the translation performance, which is only measured on the zero-shot directions, so only on the directions where we are not using English, but where we, for example, translating from German to Dutch, so all language directions, so it's averaged over all language directions which do not cover English, we see this very low performance. Then we compared the approach of removing the residual connection and disentangle the positional information, that is the third column, using an additional similarity loss or using an adversarial classifier. And we're seeing that in all of these cases, we have a very clear improvements of several blue points, and we're seeing really a lot better translation performance. Which of these methods is really performing best is not that clear. All of them have improvements. We're seeing a bit better performance by the disentangled information. However, they all help. And we're seeing that we can even combine some of them. So the best is achieved by having an adversarial classifier and using the disentangled positional information. And with this, we have really a clear, better translation performance. So this is a very nice picture, result, and it's very well motivating us. However, there's a bit of a drawback, because we can, of course, we should also compare it to the pivot-based approach, where we train our model. We again train the same one, a multilingual model, but then we didn't translate in zero-shot between for example, German and French, but we first translated to English, and then in a second step from English to the other language. And if we're doing this, the bit of disappointed is that this approach is still a very strong approach and nearly always outperforming the zero-shot cases. So we're seeing that neural machine translation and in general neural models are really sensitive to having different types of inputs and outputs, and normally they're really performing very well on scenarios where they are trained on, which in the pivot case is always the case. However, there's an interesting exception. For the Europal experiment, where we had 8 European languages and pivot always to English, we investigated how the different language pairs really performed in more detail. We see we have the baseline, which is 8.2, then we have the disentangled system, which has a lot better, and we have the pivot-based. And in general, the pivot-based is performing better than the disentangled if we average over all zero-shot directions. However, then, in more detailed, we looked at the zero-shot directions only between Germanic languages, that's the second row, or only between Romance language. And the interesting case is, in this case, the zero-shot performance is really performing better. So if we are translating between two similar languages, it can somehow better deal with these hidden representation. And then it's better to really keep the information because they are maybe very helpful and these languages are similar. And we are losing if we are first going to English and remove all the similarity and then go back to our original language. So for similar language, the zero-shot approach is a very interesting idea. We also looked into this in speech translation, where we have a similar scenario. However, in this case, we have different modalities. So this is like on the COVAS data, where we are doing speech translation. And again, what we have is on the one hand ASR data on the source side, and we have data between source and target on purely text data. And then if we want to do direct end-to-end speech translation from the source language audio to the source, to the target language text, we are seeing if we don't have end-to-end data, that doesn't really work, neither with a baseline nor with a system where we try to make the representation, in this case, the representation on the source language between English, between the audio and the text, the same. However, if we are looking now we are continuously adding more end-to-end data, and we are seeing we really in the baseline need a lot of the data in order to get a good performance. However, if we only have 20% of the end-to-end data, because this is normally much more difficult to get, we're having already quite a good performance on the with a similarity loss, which we didn't have if we don't have that. So also in these cases, like increasing the similarity improves the quality of translation. And finally, we can now also analyze how similar our representation is. And on the left side, you see again how good it was. Our classifier is able to identify the source language. And this is the picture you saw at the beginning of the presentation. We can do now the same thing with a model where we remove the residual connection. And in this case, we are seeing that, yes, in most cases, it's still able to recover. However, it does a lot more mistakes. We see a lot lighter color on the diagonal where there's like all the correct classification. And we're seeing a lot more misclassification, especially in similar languages. So, for example, between Spanish and Portuguese, but in the third one, Spanish is also like mixed up with French and Italian. And German, for example, we have a little bit of mistakes with Dutch. So we really see also similarities between languages where like humans would also think these languages are somehow similar. Okay, this was the first investigation. How can we enable like neural machine translation to change, like to recombine their abilities by using continuous representations. On the other hand, we also saw that like pivot is still a very good thing. So maybe having some type of discrete representation between that is not only a disadvantage, but can also be an advantage. Therefore, in an additional study, we investigated if it is maybe helpful to also have discrete representations in a neural machine translation system, because it might be that discrete representations are more robust. But in order to not have the problem of ambiguities as we have in a pivot language, the question is, can we automatically learn some type of discrete representations that is then more robust and that is able to be interpreted? So the idea is, if we have a source language, we are mapping the language to some integers, and we can do that for all languages. And hopefully this mapping will be again somehow language agnostic, so that, yeah, the source sentence and the translation are both mapped to a very similar sequence. So the question is, how can we learn these discrete representations? So the idea was, we have our hidden representations from the encoder. And then we're doing a nearest neighbor search in a fixed set of possible, in our code book, so in a dictionary, where we have a fixed number of vocabulary entries, and each one has also a hidden state. And then we're searching, okay, for this hidden state, what is the nearest word we have? And then we are replacing each hidden state by this nearest word. So then, of course, we at the end of the encoder have again a hidden state, which is very good, because then we can continue as normal with our decoding. However, between the output of the encoder and the information which we are giving to the decoder, we are doing this discretization, and thereby really having a discrete representation by this learned codebook. So, yeah, how can we learn that? So first of all, of course, if we are doing this discretization, we should minimize the discretization error. Because if we're doing this lookup and then we're having a discrete representation, we're introducing an error. But if this is too big, then there's no information transported from the source to the target. And that, of course, would make the translation system fail. So what we are having is an additional loss, that this hidden representation and the nearest neighbor here for each of the hidden representation, the difference between should be minimal in order to really learn a good type of codebook. Secondly, one problem is, of course, that we have one discrete step now in between, and then we can't do backpropagation, and that means we can't learn our model, which, of course, is no solutions in neural machine translation. So we looked into, okay, how can we do that? How can we still learn representations? And there we were motivated by the idea that the nearest neighbor we found, our discrete representation, and the hidden representation should be as similar as possible. And then we can do what is referred to as a straight-through estimator in the literature. So we're just copying our gradient, and we're just assuming these two representations are exactly the same. Finally, when training the systems, we of course saw that these models are less expressive, and thereby they are leading to additional errors, and therefore the system might be worse, and especially might not be as good as training. So we found out that it's better that in training we are not always doing the discretization, but we're doing what we refer to as soft discretization. So sometimes we are doing the discretization, and sometimes we are directly using the encoder hidden states. And finally, where the system still tend to lead to index collapse, that means that all hidden states are then, we search for their nearest neighbor, it's all the same. And then, of course, no information are transported. So what people have suggested then is slicing the codebook. That means that we're not searching for each hidden state one nearest neighbor, but for the lower dimensions one, and then for the next n dimensions another nearest neighbors, and so on. And thereby we're able to then learn not one discrete representation for each hidden, but maybe 5 or 8. And then we were able to get a lot better and be able to train this model really. We evaluated the system again on the zero-shot translation quality. And this time we initialized our system with a pre-trained neural machine translation system from Meta, the MM100, which is able to translate between 100 languages. And then in fine-tuning, we trained our model on a different bridge language. So the zero-shot directions we were interested in were all from Southeast Asia, and from the evaluation campaign about this. And we once looked into what happens if we have English as bridge language. In this case, we have more training data, or if we have Indonesian, where we have less training data. However, the languages are more similar. And we're seeing in the baseline, but also in all the others, that really the selection of the baseline is essential. So the performance is significantly better when we have a similar language than when we have English. However, with our techniques, we're at least making this more similar, and we're able to, again, improve the quality significantly, first with the continuous ones, and then in the last step, we have the discrete, which is not performing as good, but similarly good. However, we have, of course, some advantages. For example, that the representation is understandable. We can use that to maybe do additional analysis. We also did that on how similar the representations is, and so on. And therewith, I would like to conclude my presentation. So what I talked today about is that normally we assume for encoder-decoder models that we have end-to-end training data. In machine translation, that we have text-to-text data between the languages, or in speech translation, end-to-end, that we have audio in the source language and text data in the target language. However, this is not often the case, and in this case, what we can do is that we use multitask learning. However, to be able to perform very well on zero-shot direction, it is essential that we have compatible representations, and only in this case we're able to really perform recombine the abilities of the model and then perform tasks which we have not seen during training. And in order to achieve that, I presented you different techniques how this can be done by using similarity loss, by using an adversarial loss, by changing the architecture, or by having discrete representations. The work I presented here was mainly described in these 4 papers here. And although I wasn't personally here, I'm of course very happy if you try to reach me by email. I want to thank all my team at KIT who did most of this work. And I'm very happy if you can give me any feedback, and please free to contact me either by my email address, or you will find all the information also on the website.